We take a vector in 3 dimensions. We write as A equal to A1, A2, A3. Then this A1, A2, A3 are component of the vectors, are components of vector. Mostly they are real numbers. We'll discuss the vector value function. There this will be the function, but here what we are discussing now in this portion, that's the real numbers. So if as we have seen here, our A is OP, a very special form, we're not having PQ. Now this point is 0, 0 and 0. O is on the origin. This vector OP, when the initial point is on the origin, is called position vector. It's called position vector. So any position vector, if this point is A1, A2, A3, the position vector will be the components vector notation A1, A2 and A3. That will be the vector notation for that one. So new idea we have introduced, the idea of the position vector. Position vector is whose initial point is at the origin. We have the initial point is at origin. So we call this one as a position vector, number 1. Number 2, we can add 2 vectors. I have the vector A, number 1, addition of the vectors. We are having here 2 vectors. Vector A is equal to A1, A2, A3. We are having vector B. I take the vector B as B1 in 3 dimensions, B2, B3. I want to add it. I add here A plus B. So here I add component wise, like we add in case of the matrix. In the matrix we add the components, corresponding components. So the corresponding components of A is B1. So we say A1 plus B1. We are having A2 plus B2, and we are having A3 plus B3. So this is my additional vector. So then I am having here number 2, scalar multiplication. Scalar multiplication, that we are going to multiply a vector with a scalar. For example, I have this vector A. I have here A1, A2, A3, and K is a scalar. K is scalar, is a real number. I want to write here Ka. So Ka means K into vector A is A1, A2, A3. We say we multiply each of the component with vector A, Ka1, Ka2, Ka3. That's my result. That we call this scalar multiplication, that we can multiply a vector with this scalar K. So that's the idea for multiplication. Then I just take here number 3. When 2 vectors are equal, we say we have vector A and B, as mentioned in 1. We say is equal to B. That means A1, A2, A3 is equal to B1, B2, B3, B3. If we're having they are equal, if we're having corresponding entries equal, corresponding entries A1 is equal to B1, A2 is equal to B2, A3 is equal to B3. We say these 2 vectors are equal. So is the number 4, the negative. We can multiply vector A with -1. So we have minus into A1, A2, A3, then each of the entries multiplied by minus. Minus A1, minus A2, like the matrix we do, when multiply matrix with a number, the whole of the matrix elements are multiplied by that number. Then we are having here 0 matrix, 0 vector. 0 vector is a vector whose all entries are 0. So we have 0 vector is equal to 0. It can be 2 dimension, it can be 3 dimension, and it can be of any dimension. We can say this is equal to. Then is number 6. We are having A dot A. So we will be discussing later. Then we have already discussed the magnitude of the vector A. So as we defined before, the magnitude, as we have defined before, that is equal to square of the each element we defined by this way. And what is that one? That is here is equal to A1 square plus A2 square plus A3 square. That's the magnitude. Number 7 is the direction, or we say the unit vector. unit vector. Unit vector is vector u whose magnitude is equal to 1, and we divide vector a by its magnitude. So these are the properties we have already discussed and mentioned it. The new property is that addition of the two vectors, this like just the matrix, multiply is a scalar, that's we multiply by k. Then the important point was position vector. If the vector is initial point is at the origin here, and we say this is our position vector. If is there any other point place, another place like here is AB, so this is not the position vector because A is not at the origin. If A was at the origin, then we say this is our position vector. So here we can just introduce one more idea that we can just write the vector in different form. This is our vector in 3 dimensions. We have these components like A1, A2, A3, and we have already defined our unit vectors. So I just write this vector very interestingly. So you can see it here, this is A1. I write my A is equal to, because we can add, we have A1, 0 and 0 plus 0, A2 and 0 plus 0, 0 and A3. So we can just write it like this. Why? Because we can add it. A1 plus 0 is our A1. 0 plus A2 plus 0 is our A2. 0 plus 0 plus A3 is our A3. So we can write like this one. I take A1 common. I write here A1. I get here 1, 0 and 0 plus here I take A2 common. When we take A2 common, then we are having inside A2 common. We get here 0, 1 and 0. We take A3 common. We get here 0, 0 and 1. So what's this one? I know it. This is my I, the unit vector, is equal to 1, 0, 0. J, unit vector along y-axis, 0, 1, 0. Unit vector along z-axis, 0, 0, 1. So I can write it here. This is equal to A1I plus A2J plus A3K. So any vector we can write in terms of the component form or in terms of the unit vector. We take an example. Example, write in component form. Our vector given to us is vector A. Vector A is equal to 2i minus j plus k. So this is my form. This is unit vector form. So what's my I in component form is equal to 2 minus 1 and 1. This is component form. Another example, I'm having here the vector B. My vector B is equal to I plus 3k. So what's the component form? B is equal to the component of I is 1. There is no j, so that will be 0, and the coefficient of k is 3. So this is 1, 0 and 3. We given the component form, we can write the unit vector form in terms of unit vector. We given here another example. We are given here C. C is equal to 2 minus 1 and 7. We can write here C is equal to 2i minus j plus 7k. So given in terms of the both are equivalent. Both forms are, the value of the vector is same, they are equivalent, there is no change in that one. I'm going to give you the example in which we will use all the ideas we have just developed as the properties of the vectors. So this my example is that we are given two vectors A and B. We want to find the addition, subtraction, and then scalar multiplication and subtraction magnitude of this one. We take number 1. We are given vector A and B. So I have this vector A is here minus 2, 6 and 1. And we have vector B. Vector B is equal to 3, minus 3 and minus 1. So we find here A plus B. So A plus B is components by addition. This A1, B1, this minus 2 plus 3. Then I have A2, B2, 6 minus 3. This is my 6. Make it more clear. Here is 6. And then I'm having here A3, B3. This A3 is 1, B3 is minus 1. We simplify this one. We get here 1, we get here 3, and we get here 0. This is my A plus B. Number 2. My next is A minus B, so I have to define minus B. My A is very clear, my A is same, minus 2, 6 and 1. Then I have my b is equal to 3, minus 3 and minus 1. I define my minus b, multiply this one by minus, we get here minus 3, 3 and 1. Now I can define a minus b. A minus b is equal to a plus minus b. We add these two vectors, this a and minus b. So we get here this is equal to minus 2, minus 3, minus 2, minus 3, and then we have 6 plus 3 and 1 plus 1. So the result I'm going to get here is minus 5, 9 and 2. This is my a minus b. The next is I want to find 5a minus 4b. So to do that one, first we have to find 5a. So I multiply my a with 5. What's my a? My a was minus 2, 6 and 1. I multiply this one, I get minus 10. I get here 30. I get here 5. Each of the components will multiply by 5. And multiply vector each of the components. And 5 is a scalar and a is a vector. Then I have minus 4b. So I multiply my vector b by minus 4. So I have minus 4. What's my b? My b is 3, minus 3 and minus 1. So each of the entries multiply minus 4. We get here minus 12. We get here 12 and we get here 4. Now I have 5a and 5b. I can write here my 5a minus 4b is equal to 5a plus minus 4b. So minus 4b is a new vector. We add this one. This is my 5a and this 4b is 10 minus 12. Minus 10 minus 12. Then I have 30 and 12. This is 30 plus 12. And then it's 5. And then here minus b is become here 4. And when just add this one, we get here minus 32. We get here 42. We get here 9. So it's my result of third part, that is 5a minus 4b. We go to number 4. I want to find the magnitude of vector a. So my vector a is having the components this is equal to minus 2, 6 and 1. And I want to find the magnitude of this one. So magnitude of this vector a is under the root of a1 square minus 2 whole square plus 6 whole square plus 1 whole square. So we square it and add it. We're having the under root sign. We get here 4. We get here 36. And we get here 1. So this is equal to root of 41. So that's my magnitude of vector a. So the next one is I want to find the magnitude of vector 3a. So I have a. My a is equal to minus 2, 6 and 1. I want to find here 3a. So my 3a is 3 multiplied by minus 2, 6 and 1. I just multiply it. We get here minus 6. We get here 18. We get here 1. So magnitude of 3a is square of each of them, square of minus 6 whole square plus 18 whole square plus 1 whole square. So we just take the square of this and we add it, and we'll get here the result of this one. This is equal to, here is I multiply by 3, that's become here 3, and also here is 3, and we get here 3 whole square. And we take the root sign here. We get here 36 plus 18 whole square will be equal to 324. And then we get here plus 9 under the root. We add it. We'll get here the result of this one is equal to 369. So I take as this result, my result as 1. I write a result as 2. I get the relationship between these two. I can write here magnitude of 3a is equal to, here I get here 9 multiplied by 41 under the root is equal to 9 under the root into 41 under the root. 9 under the root is 3 into 41 under the root. And we can write here this is equal to magnitude of absolute value of a is 41. So this is equal to 3 into magnitude of a. Or we can write here magnitude of 3a. We can write here this is equal to 3 into magnitude of a. We don't need to do all of this. We just multiply this one by 3 taken inside become 9, and we get the result as 369. We come to this example. we're given a vector A, 2 multiplied by minus 2, 5 and minus 1. We want to find the unit vector. First we multiply inside and we divide this vector A is equal to 2 multiplied by minus 2 is 4, 2 multiplied by 5 is 10, and 2 multiplied by minus 1 is minus 2. So this is my vector A. So the unit vector, I say the direction of A. What's my unit vector? My unit vector, I denote it by U, and this is here is A over magnitude of A. So write the unit vector, I need magnitude of A. So I write here magnitude of A is equal to root of 4 whole square minus 4 square is 16, 100 whole square, 10 whole square is 100, and here is plus 4. So the result of this one is 120. So this is my magnitude of A. So I can write my unit vector. Unit vector is 1 over the magnitude of A. This here is 1 over the magnitude of A into vector A. This 1 over 20. The vector A is our vector minus 4, minus 10, minus 4, 10, 10 and minus 2. We can write this equal to, we're having here minus 4 over root of 120, we're having 10 over root of 120, and we're having minus 2 over root of 120. So this is my unit vector. So this is the idea of how we can find the different algebra of this one I've just mentioned here, and we can find the unit vector. This vector was not was outside, so we just multiply by 2 inside, and then we can write the magnitude of this one, and then dividing the magnitude by vector A by its magnitude, we get the unit vector.